Today we will see a analysis pertaining to the topic of passive filters. Okay. I said passive because there are active filters also. That's why this will act as an introduction for active filters and also used in the exam directly also. So it has two purposes: to answer the questions directly in the exam under this passive filters, or this will be useful in active filters. For example, why I say passive is we use passive components. What are the passive components? RLC components. So when we see RLC components, they don't produce any amplification. That's why it is called passive filters. Let's go to some fundamental definitions and classifications, then design equations, then finally some problems. This is a normal approach for this. So we can see some previous exam papers also. First definition: the electrical signal contains many frequencies. In that, to suppress unwanted frequencies and to pass desired frequencies, filters are used. Please remember, signal means more than one frequency. By the characteristics of signal, it has to have more frequencies. So when there are more frequencies, some of them has to be allowed, some of them has to be suppressed. That is called filter, the purpose of the filter. Then second definition is characteristic impedance. We call it as Z0. It's the impedance offered by the network at one port, and it is terminated with the same impedance at the other port. For example, if that impedance is there at the output port, if the same port impedance is applied, then we call it as matching. So one should know how much impedance it is offering. It is the impedance offered by the circuit. So we call it as characteristic impedance. Sometimes we call iterative impedance. And when we say iterative impedance or impedance at the seen at the ports, load impedance. So this impedance, if you terminate with the same impedance, what happens is you will have the impedance equal and then maximum power is transferred. Now let me take an illustration by taking a problem. Calculate Z0 for the symmetrical T circuit shown in figure. So we have to calculate characteristic impedance of different circuits. I call it as symmetrical because we are taking Z1 by 2, Z1 by 2. It is a T network because it is in the shape of T. So we need to calculate the impedance offered at one of the port. Let us see, that is the question. The solution goes like this. Characteristic impedance is root of short circuit impedance multiplied by open circuit impedance. Short circuit impedance, let us calculate. Look at here. This is shorted. These two are in parallel in series with this. So ZSC is equal to Z1 by 2, Z2, Z1 by 2 by Z2 plus Z1 by 2. This is what the impedance we have. Similarly, if you calculate open circuit impedance, what happens? This is doesn't consider, it will not come into the analysis, only these two come. So Z1 by 2 plus Z2. This, if you multiply this impedance and this impedance, the numerators will be simply cancelled. Observe here, Z2 plus Z1 by 2, Z2 plus Z1 by 2 will be cancelled. And then you have to see Z1 by 2 plus Z1 Z2 by 2. Then if you take under root Z1 Z2 plus Z1 by 4 Z2, this is what will come. This is called characteristic impedance of T network. Similarly, we can also calculate characteristic impedance of pi network. Let me take another problem there. See problem 2. Calculate Z0 for the pi circuit shown in figure. This is also symmetrical. Why do I say symmetrical? 2Z2, 2Z2. See, if you take parallel combination of 2Z2, 2Z2, it will become Z2. Similarly, if you go for the serial, Z1 by 2, Z1 by 2, if you add it, it will become Z1. That's why in series branch, we divide that by 2. In parallel branch, we multiply. That's the meaning of behind this taking 2Z2, 2Z2. Okay. Now let me calculate ZOC and ZSC. Look at here. If you short this, these two are in parallel. Z1 parallel 2Z2. That means Z1 2Z2 by Z1 plus Z2. Similarly, if you look at here, open circuit impedance, how are these things? These two are in series, parallel with this. That means Z1 plus 2Z2 into 2Z2 by Z1 plus 2Z2 plus 2Z2. This is what ZOC. If you multiply under root, you will get this. If you observe the previous problem, it is same as Z1 Z2 1 plus Z1 by 4 Z2. It's almost same, but remember one thing. There it was multiplication, here it is division. This is by. It is easy to remember also. Okay. So this is how I calculate Z0 t and Z0 pi. Next. Third problem. What is the relation between Z0 pi and Z0 t? See, Z0 t you got this as multiplied. Z0 pi you got it as divided. Now please multiply this. What will happen? If you multiply this, root and root will cancel. And what will come? Z1 Z2, Z1 Z2. This is into by. That means this part will cancel with this part. What are you left with? Root of Z1 Z2 whole square. That will become Z1 Z2. That's why Z0 pi into Z0 t is equal to Z1 Z2. Actually, this is what we normally call it as RK square. We will understand that slowly. So this is my third idea to tell you the relation between Z0 pi and Z0 2. Good. So let's go to further some more theory before we enter into problems there. Now another interesting thing I have to take problem 4. Same Z0. Now I am just defining Z0 is JX1, Z2 is JX2. If Z1 is JX1, Z2 is JX2, what will happen to the characteristic impedance for the same circuit? So take the expression in Z1, Z2 here, substitute there. Z1 is JX1, Z2 is JX2. 1 plus JX1 by 4 JX2, JJ will cancel. J square will become minus Z1, Z2, X1, X2 here, 1 plus X1 by 4 X2. Then you may ask me, where is the polarities? Because if you put plus, it is impedance. If you put minus, it is, if you put plus, it is inductance. If you put minus, it is capacitance. But at this level, I don't want to say whether the first one is capacitor or inductor. That's why the best thing I can say, the polarity is included in the reactance. Generally, polarity is included in impedance, but in this case, we are including the polarity when the reactance is involved. So look at this carefully, and I am going to make some conclusions. By saying minus here, what are the conclusions you can make? What should be the components, choice of components here? Can it be inductor, both inductors, both capacitors? One inductor, one capacitor, I need to discuss. So that is, we will be discussing in this fifth problem. For Z0 to be real, what are the values of X1 and X2? Why it should be real? If Z0 is not real, there is no power delivered, power is stored. For anything power to be delivered, the best thing is there should be no complex quantity, that's a real quantity. So minus X1, X2 greater than 0, 1 plus X1 by 4 X2 greater than 0. That means this factor should be greater than 0, this factor should be greater than 0. Why? If this factor is less than 0, what happens is you will get an under root you will get j. Negative means j square, and then it will become j after taking root. So we don't want any j terms, means first part should be greater than 0, second part as well should be 0. Therefore, for z0 to be real, x1 and x2 are having opposite polarities. Why? If x1 and x2 are opposite polarities, one of them will have negative sign. If negative sign and another negative sign is cancelled, automatically there is a very guarantee of that to be real. So first conclusion I am going to make is x1 and x2 has to be opposite. That means suppose if x1 is inductor, x2 should be capacitor, and vice versa. So this is what I mean by understanding what should be the value of x1, x2, or what should be the choice of x1, x2. So these are the basics I have developed for entering into the subject. Then you will know how to really analyze the circuits. So far I only spoke about the nature of the need of the components, the type of the components. Okay. Now I will take you for different filters. And before even there, we have relation between alpha, beta, gamma. Alpha, beta, gamma are defined in this way. Gamma is equal to alpha plus j beta. Alpha is attenuation factor, beta is phase shift constant, and gamma is propagation constant. So when you want to know when in a filter how much attenuation is there, you can know that. Attenuation should be 0 for pass band and more in the stop band. 0 is of course is expected, but that's ideal case. Ideal case may not be always satisfied. Therefore, imagine this and approach this one, that is 0 for pass band and more in the stop band, right? This is about what you call a relation between alpha, beta, gamma. When you say attenuation of a frequency can be measured in decibels or neepers. Decibel means base 10, neeper means base E. Base E means natural logarithm. Attenuation in dB is generally given as 10 log base 10 pi by p, because if you take input by output, it is called attenuation. If you take output by input, it is called gain. Attenuation in dB, suppose you want to convert into voltages, you will say by R by R. So V square by R, V naught by R, RR cancel if for matching purpose. That square comes here, 10 will become 20. That's why we generally say power ratios it is 10, voltage ratios it is 20. So power ratios it is 10. For voltages and currents you can always have 20. So this is about attenuation in dB. Then attenuation in neepers, as I told you already, log II by I naught, Vi by V naught. So this is not a log, it is a natural logarithm ln. Ln means base 10. Now what is the relation? Attenuation in dB is 8.686 into attenuation in vapors. If you want attenuation in dB, this is the answer. So this is all about introducing what is alpha, beta, gamma, because when I am talking about pass band, alpha should be 0. Attenuation should be 0. If I am taking pass band, then attenuation is 0, but output is maximum. So to know whether it is a pass band or stop band, the best way to know is alpha. So depending on the alpha, depending on the impedance, we can say that. So what is the ideal thing here? Impedance has to be constant in the pass band, and not only that, you have to have this value, attenuation should be 0, right? Now, based on their operating frequencies, filters are classified as follows. I am classifying them as 5. Low pass filter, high pass filter, composite filter. Composite actually two types. Low pass composite is there, high pass composite is there. In fact, we need to bring out something called M derived filter. Fourth one is band pass filter. Fifth one is band elimination filter. So totally we can have 5 filters. In fact, we have to study those 5 filters. So that is how we can start our classification as such, right? Now let me go by filter. A low pass filter. Low pass filter allows the frequencies below the cutoff frequency and attenuate above the cutoff. So below cutoff it is 0 alpha, after cutoff maximum alpha. So low pass means passes low things. The frequency which is differentiating attenuation band and stop band is called cutoff frequency. Cutoff frequency is where it differentiates pass band and stop band. So these are the definitions of a low pass filter. Then let us see how to really go about. For band pass, for pass band, shunt branch should be open and series branch should be shorted. That means the series branch should act as a zero resistance. That means output go. Shunt should act as open circuit. That means output will go through the series branches. This is open circuit. Hence, in low pass for pass band, XL should be shorted and XC should be open. So this is what happening as far as your definition is concerned. Now I have chosen what it means by inductor and capacitor. Remember very simply, if frequency is low, what happens to this low? What happens to this low? If same frequency low, capacitor is 1 by j omega f, omega c. That means frequency is low, this will act as high. So inductor being on the series branch, capacitor being on the shunt branch, it is acting as pass band. So it is able to pass low frequencies. That's how you need to understand. Don't mug up. For low frequencies, inductor is shorted. That's why signal comes. For low frequencies, capacitor is open. That's why it is not going to ground. Instead of going to ground, it is directly going to load. That's the basic definition of low pass. Okay. Now, XL should be short circuited for low frequency. XC should be open circuited for high frequency. Calculate this. Omega L, omega C, 1 by omega C. This is cancel. Omega, omega cancel, 1 by LC, root of this one. And this is what we call it as RK is terminating impedance and this is the actual impedance. By that what I am saying, Z0 depends on frequency. As frequency changes, impedance in the pass band is changing, which is not really expected. We are expecting a constant K filter. That means impedance is constant. Okay. So impedance is constant, but is not terminating at constant, because if I call this as RK here, and this is anyway frequency changes, Z0 changes. We expect constant impedance, but it is changing impedance. That's why we are not happy with constant K filter. Very interestingly, a filter which is called constant K, impedance is never constant. They thought originally impedance is constant, that's why they named it as constant K filter. But after doing it, they understood there is a frequency component here. You can understand Z0 is changing with respect to that. Okay, that's called terminating impedance. Let me give you an equation. Now 1 minus omega square LC by 4 is equal to 0. Why? This portion is, when this is portion is 0, we call it as cutoff. What do you mean by cutoff? Pass band, stop band, center is cutoff. So omega C is 2 by root LC, FC is 1 by pi FC. See here, from here I am doing it. 1 is gone, omega square LC, 1 by LC. Then 4 goes there, 2 by LC. So 2 by root C. And what is FC? 2 by root LC into 2 pi. 2 cancel, 1 by pi LC. So this is how we got the capacitance called cutoff frequency. With this capacitor and given our RK, L is RK by pi FC, C is 1 by pi RKC. Then what is Z0? 1 minus F by F in FC. This is into Z0 pi is divided by. That means what? When this is increasing, when F is increasing, this quantity is increasing, 1 minus increasing is less. 1 minus increasing is less. So RK into less. This is RK into more. RK by less. This is by less means it becomes more. So you have two ways of calculating. So we are getting cutoff frequency here. We are getting L, we are getting C, Z0 T, Z0 pi. This is all about the impedance characteristics of a filter. Now, if you are talking about low pass filter that allows frequencies below cutoff and attenuates the above, that means this you see here, pass band, rejection band. This we can call it as a stop band. This is suddenly sharply falling. Is it possible to sharp fall with alpha? Impossible. That's why this is called ideal characteristics, whereas this is called practical characteristics. So ideal characteristics is here, practical characteristics is here. Okay, that's about low pass filter. Then I will take you for high pass filter. High pass filter are allowing high frequencies, attenuating low frequencies. Before we enter into too much of mathematics, always go for protocol to explain what it means by how it is called high frequency filter. These high pass filters are allow the high frequencies and attenuate the low frequencies. Here this value is 2C because when you take series branches it is 2 times of that. Because capacitance is series, if you bring 2C and 2C they become C. When you take inductor you should take L by 2, L by 2. That's about high pass filter circuit. A circuit with CL is called high pass. Circuit with LC is called low pass. So enjoy the same concept. Z1 is 1 by j omega c, Z2 is, because now it is interchanged. This is Z1, this is Z2. So if you substitute these values in this characteristic impedance, you will get this way. Now once again equate this value, you will get the frequency. So by equating this value to 0, you will get the frequency, but Rk is root of L by C. So Rk value I am taking L by C here. So when there is an impedance, characteristic impedance depends on frequency now. If I convert this frequency into cutoff frequency, what comes? See there, ultimately this is what you get. So if I really calculate cutoff frequencies from the expression of Z0, this is how you will get L, LC and Z0, Z0 pi. These are the frequencies we have. This is the equations for design. Equations for design is this. Okay. Now we have finished low pass and we are coming to high pass now. This is ideal filter. Now what is happening? Exactly opposite. Pass band is in the higher side, rejection is in the lower side. Stop band, pass band. So this is what it means. Pass band, stop band, pass band, stop band. So these are the introductions over. Now I am going to talk about constant K type filter. Why do I say constant? I say constant because Z1, Z2 will become K square, that is called R0 square. R0 is characteristic impedance of the section. Therefore, if you say something called K, which is called K square, because of that K which is constant, this is called constant K type filter. So that's the meaning of constant. So this constant K filter is also called prototype filter, please. And you know why it's called prototype? Because for any big filter you want to design, first design the prototype. Prototype means, English meaning is model. First develop the prototype. From the prototype you develop anything. For example, develop the prototype. From prototype you develop M-derived filter. And that's why this is called prototype filter. Developed one is called M-derived filter. That's how you can always design a prototype and keep it ready. According to purpose, we can extend the value there. So it's called constant K filter. What is the characteristics? Just like we said, Z0 pi, Z0. This is pass band. That means this is basically low pass filter, pass band. But please observe, the impedance is no more constant, it is changing. When impedance is changing so much, we can never understand how they can help us to have a constant k. So we are calling as a constant k because we assume that throughout any frequency impedance is same. But as the frequency changes, impedance is changing. That's why we are unfortunate to say it's not keeping up its own word. Constant k filter means it should be constant, but it is changing now. So this is what I mean by the word called constant k filters. Okay. Now what are the advantages? Attenuation does not increase rapidly beyond the cutoff. See, once you enter the cutoff, low pass is allowed, high pass has to be eliminated. So how fast it should eliminate? It should raise suddenly, but that's not happening. And the castic impedance does not remain constant during the pass band and causes reflection losses. It's not constant. That means it's changing with frequency, as we saw in the diagram, like this. So constant k is not behaving like a constant k. The very purpose of calling a constant k is because the impedance is constant. But unfortunately, that's not happening. So it causes reflection losses. Okay, right. That's about constant k filter. Let's go to the next one called M-derived filter. For the drawbacks that we have seen in constant k filter, the solution given by Jobel, his name is Jobel, he brought an idea and he brought the filter called M-derived filter. When it's called M-derived, don't think it is simply M. M is an operator value. That's why he called it as M-derived. He brought a factor called M, root of 1 minus Fc by F infinity whole square. So what he is going to do in that? He is going to produce one factor called M here. With that, he is going to bring out another filter. That's why I told you constant k filter is called prototype. We'll take the prototype filter. From that model filter, we develop M-derived, we develop M-derived offsection. In fact, we can also develop band pass and band elimination. And if you know, this called designing one filter and translating it to another filter, that is what exactly we do in digital signal processing. Now, because students are not studying this translation of one filter to other filter at the passive filters, they are not able to understand active filters and they are not able to understand digital filters. But the very idea of the filters is all the three same. But unfortunately, this designing the prototype and translating it to band pass and band elimination, nobody is doing, but at least let us see how it is translated from prototype to M-derived. So this translation concept of the shifting, designing the lower filter, shifting to the higher filter, that has come even in DSP. For example, you will design a filter using Windows and then you will translate it. That's called IIT or BLT. So once people understand these concepts of translation in passive filters, they can easily understand in digital filters. So this is how one has to appreciate and learn the filters in passive, learn then going to active, finally going to, that's called digital filters. So once you know one type of filter, the rest of the filters will be easier, right? Now let's concentrate on M-derived filter, that the Jobel, how he has done it. Look at here. This is the equation for M-derived where Fc is cut off F infinity. But please understand, M is generally between 0 to 1. My best way of making you to remember is, this should be always lesser, this should be higher. Lesser by higher will yield a factor there. Lesser by higher will leave a factor there. For example, low pass filter, cutoff frequency is 1 kilo, F infinity will become 1.2 kilo. That means 1 kilo by 1.2 kilo will become smaller, 1 minus smaller will become a smaller. All that, no negative term, should be there. If there is a negative term here, you will have J term incoming. Such a thing should never happen. So Fc's cutoff frequency, F infinity is a frequency at which attenuation is infinite. Right. For m is equal to 1, M-derived filter becomes constant phase. For m is equal to 0.6, It's good for almost constant impedance. Please remember, as I said, you need all the three filters. M derived is required to give a sharp rise in the alpha in the stop band. Sharp rise in alpha is by M derived, but it only raises, it doesn't keep it constant. To put it constant, you have to go for constant K filter. Then after that, what about impedances there? That's possible only by half section. Therefore, it's not that we need only M derived, we need M derived, we need a constant K, we need a half section. That's why it is called combination of all the three, it's called composite filter. So when you say composite filter, the meaning is this. So look at here, the impedances, how they are going. You look at here, constant K, M is equal to 1 means what I said? Constant K. This impedance is changing very badly. When you say M is equal to 0.6, impedance is slowly rising. So M is equal to 0.6 is better than M is equal to 1. That means M is equal to 0.6, it means half section. Half section is better than constant K. And you look at M is equal to 0.4, M is equal to 0.2. You know what are these things actually? These belong to M derived filter. That means M derived filter is become worst as far as impedance is concerned. Here that's why the best is half section, maybe the better, somewhat okay is constant K, but M derived is worst of all. So M derived, the purpose is not for impedance, it is for alpha, attenuation to increase sharply. That's why we call infinity. Infinity is to tell that at this frequency alpha becomes very, very high. So these are the descriptions and these are the ideas under which I am going to make, or when Joubel has made his filter called K. So now let us see M derived filter by Joubel. What Joubel assumed is Z1 dash is equal to MZ1, he said. And then because Z0 T should be equal to Z0 T dash. What does it mean? This is constant K impedance should be equal to M derived impedance. Constant K impedance and M derived filter impedance both are equal, should be equal. Otherwise, the very purpose of conversion should not affect the impedance. Therefore, you have this impedance. This is called constant K and this is called M derived. If you equate them, you will calculate M Z2 dash. That is 1 minus M square by 4M into Z1 plus Z2 by M. Then this is all about Z2. That means second branch is going to have two branches now, whereas the first branch has only one. So first branch is having one arm, second branch is having two arms. That's what exactly M derived filter is telling us, right? Now look at here. As I said, M is equal to 1, this date. This is M is 0 to 1. Can you please observe, whenever you got a doubt, the best way to cross check your M derived filter is put M is equal to 1, this should become this one. M derived should become constant K when you put M is equal to 1. Can I help you? MZ1 by 2 will become Z1 by 2 and 1 minus M square becomes 0. When M is equal to 1, 1 minus 1 is 0. That means this is disappearing. That's what happens, you see. Z2 by M becomes Z2 by 1. This is. So when I put M is equal to 1, please remember M derived filter becomes here. So that's a very interesting, a very serious way to remember all this. You don't need to be panicked to remember this. By mistake, if you get any doubt, put M is equal to 1, you will get back here. Let's go to third heading of composite filter. As I have discussed all the three filters brought into one, as I already told you, we need constant K filter to maintain alpha, whereas M derived filter is to achieve sudden increase. Half section is to maintain impedances. So when you look at these three, so M derived is here, constant here, half section here, half section here, impedance. Why should we put the half sections at the end? By keeping the half sections at the end and the beginning, you are maintaining the characteristic impedance in a constant way. That's why they must be at the end of this one and end of that port. This is how the word composite filter came, because you are using more than one filter. Composite means more than one. So this is about my concept about third filter called composite. First one is high pass, second one is low pass, third one is composite. Fourth point, band pass filter. Band pass means it pass only the center one, below and after it will alternate. That is band pass filter. Then how do we get that? By cascading high pass filter with low pass filter. When you cascade, you see this comes here, this comes here, this comes here, this comes here. These two are here. So then what are the equations involved? As we said, these are the equations for low pass and high pass. When we cascade, low pass L1 C2 belongs to low pass, L2 C1, C1 and L2 acts as high pass. So look at this. So when you say low pass, you will have pi. When you say high pass, you will have 4 pi. Easy to remember, I am telling. Then if F2 is greater than F1, it's called band pass filter. If these two are equal, it will pass a narrow band. It's also called beat frequency because two frequencies are coming at the same. And then if F2 is lesser, some people are thinking by mistake band elimination, but that is no pass filter or all stop filter. Because I have ruled out cascading can never give band pass. Please remember. Under any circumstance, whether it's F1 is lesser or higher, doesn't matter. If F1 is lesser, you get a band pass. If F1 is greater, you will get no pass. Right. Let me go to band stop filter. This filter attenuates the frequencies at the center. Other two are passed. So how do you get it? That you get by cascade, not by cascading, but by connecting in parallel. So this is low pass, this is high pass. When you connect them, you can easily observe these two are here, these two are here, these two are here. That becomes parallel. That becomes band elimination filter. Equations are also same. For low pass and high pass, we already know equations. Then what best you can think is L1, C2. They become what? Low pass. That's why pi and pi. C1 and L2 becomes high pass. They become 4 pi, 4 pi. These are the design equations involved. If F2 is greater than F1, we get all fish. If F2 is equal to this narrow band filter, that's called notch filter. F2 is less than F1, we got band pass, band stop filter. So these are the three possibilities with the same filter. I've already discussed about 5 problems. Now the 6th problem comes. Obtain a low pass filter for FC and RK given. Remember, sometimes people call this RK as iterative impedance, characteristic impedance or image impedance. So feel free to have that. Then this is the filter design circuit as we already discussed. These are the equations to it. So therefore, this equations 53.07 milli, 212 nanofarads will come. By designing this, for example, this is 53, but what you should substitute here? 53 by 2. So this is called low pass filter. As I told you, it is a constant K filter. Using this filter, I am going to design any other filters. That's why it is called prototype. Next, 7th problem. Obtain high pass filter for the cutoff frequency TK, RK is 500 ohms. So follow the formulas that we discussed earlier and then you will get this value. What I am trying to say is once you get C, don't put that C. You have to multiply with 2C. So this is what about high pass filter design. 8th. Obtain composite low pass filter for FC 1 kilo, F infinity 1.2, RK is 5. Look at here, half section, prototype, M derived, half section. So in all these things, you need to design or learn only 3 things. What is M? What is L1? What is C2? Design of components only 2. That's why L is here, C is here, M is here. Substitute those values. Just like low pass, I am derived here. As I told you, if M is equal to, then what happens here? We should put M is equal to 1. It's already taken care. And here I did not mention there in the problem, but please remember, while designing off section, we'll say M is equal to 0.6. M is equal to 0.6. So whatever the M comes, we substitute here. M is equal to 1 here, M is equal to 0.6 here and 0.6 here. That's the design that we have. Let's go to 9th problem. Obtain the band pass filter for F1 and F2 is given to 3K and 5K, RK is this. As I told you, it is a matter of cascading of low pass and high pass. Then you need to, you need to design the formulas which you have already given. Solution. L1 and C2, C1 and L2, they come here. So after designing these values, please understand, once you go to circuits, you are not going to put the same L1, you will put L1 by 2, not C1, 2C1. That's why design the values, put in the circuit according to the circuit formula. Let's go to 10th problem. We need to design band elimination filter F2 3 kilo, F1 5 kilo, RK is here. This is a circuit we know, and these are the formulas we know. And calculate them as we already discussed in the theory, substitute according to the circuit arrangement. Remember 3 things when I am doing problem. The equations that are there in the theory that I have discussed already, and you use this data given by the problem. But after calculating element, don't think you can substitute as it is. Sometimes you have to put the twice of it or half of it, depending upon the arrangement. That's all about band pass. Now let me show you some problems given in the exam. The circuit shown in figure represent what? Is it a low pass, high pass, or band stop? Given in GATE 2000. So for anything is given, you have 2 approaches. If the circuit is simple, go for a transfer function. From the transfer function, you can easily identify whether it is which filter it is. If you have 2 cutoffs, band pass or band elimination. If there is only 1 cutoff, low pass or high pass. So you can easily identify. That is one approach. Second approach is just see, put the frequencies, draw the equivalent for low frequency, draw the equivalent for high frequency. If it is allowing low frequency, call it as low pass. If it is allowing high frequency, call it as high pass. If it is allowing low both, then you have to say whether it is band pass or band elimination. Then it all depends on F1 is less than F2 or F1 is greater than F2. Shall we look at that? Let's go to the solution. For band pass, normally for anyone to have a pass band, shunt series element should act as a short circuit, and shunt element should act as a open circuit. You see there? When I give low frequencies, this will act as a short, this will act as an open. So low frequencies are coming. When low frequencies are coming, then for high frequencies, how is the circuit? This is coming. So I have drawn the equivalent for low frequency, I have drawn the equivalent for high frequency. Then let me conclude. But at cutoff frequency, it will never have operate, and hence the circuit given will operate as band stop filter. That means at the cutoff is not working, therefore other 2 are working, so it is called band stop. Maybe if you can further talk, if it is only cutoff is missing, you can as well say notch filter instead of saying band stop. So remember, notch filter came many a times. I'll be talking about the notch filter when I go to 2-port networks, which I am going to take after or soon after this lecture. So that's about option. Your option is D. Problem 12. The circuit shown in figure represents, and that's given in GATE 2007, and you need to identify which filter is that. Remember, we have 4 filters. All the 4 filters are given every time, A, B, C, D. You need to understand. So this best thing I am going to do is I'll take a transfer function, as I told you. When the circuit is simple, I'll take a transfer function. Let us see the transfer function. When you take the transfer function, output by input, you will get this one, and if you put the cutoff, the frequency response is given here. When the frequency response is given, as you understand, it is acting as BPF. Therefore, option is band pass filter, that is C. Then last problem. A waveguide can be considered to be analogous to which of the filters of the four? It's given in IES, but for EEE it is very surprising, because waveguide, the word, even EEE people do not know. I don't know why it's given, but the answer we can easily understand. Waveguide means high frequencies. If it passes high frequency, we call it as a waveguide. So the option straight away is B. So this is all about filters, but please understand, I have taken in all my considerations except in one or two sides. All others I have taken T section. If you want pi section, you can go for same approach you apply for phi section, because repeating two things will be laborious. Therefore, a student is advised to go by himself. What happens, it's a low pass filter with pi, high pass filter with pi sections, you can study, but the approach is the same approach will be applicable for pi network as we did in T network. This is my, you call it as assignment or you call it as homework. Think on that and get ready for the exam. Good.